I'm presenting you Katherine Jarmul. She's an American living in Berlin, so not the other way around as it usually goes. She told me she's about to get a permanent residency in Germany, leaving the States behind probably. Katherine's been very active in the big data community. This is where she actually comes from. This is where people know her. She's a conference organizer herself. But lately, she turned to machine learning and artificial intelligence. She even started a startup on artificial intelligence protection or security of artificial intelligence processes, companies, ideas. And we at Swiss Cyberstorm, we usually try to steer clear of the buzzwords. So we've never done a machine learning talk before, as far as I remember. We haven't done artificial intelligence. We still steer clear of anything blockchain-y. No blockchain talks. This year, I mean, imagine that. And we had a lot of requests, can I present blockchain security to Cyberstorm? I said, no, that's too new, that's too fashionable. We'll wait for a couple of years. But it's about time to get going on machine learning security. And what Katherine is going to present us really surprised me. I never thought of this vector for privacy attacks. Thank you, Katherine.
Thanks so much, Christian. So, if you came here for only a talk on adversarial examples, I hate to inform you that we will also be talking about privacy in machine learning systems. So hopefully I'm surprising you a little bit, and we'll talk about both privacy and security in machine learning systems as they're currently deployed today. And the first thing I must address, of course, anytime I speak to a non-machine learning community audience or a non-data science community audience, is AI, is it hype or substance, right? I must address this because unfortunately lots of marketing people at big companies that do really good machine learning tend to wrap AI as some sort of magic, as some sort of cure-all for a bunch of things that it doesn't do, and even tend to use the word AI when they're simply describing standard statistical methods or machine learning models. And so what we do is not magic, it's just math. And it sometimes doesn't work. So this tweet, I basically spit out my coffee laughing because indeed, this robot that most likely uses some form of computer vision has a lot of trouble with hedges. And whenever it sees a hedge, it stops because it doesn't know how to proceed. And so the way to protect ourselves from robot overlords is to build more hedges, right? This is one possible way. And when we think about what we want to use something like AI systems or machine learning systems for, we have to overcome these types of real adversarial examples in real life. But you may also be familiar with adversarial examples as they're so called within machine learning research. And one such is this adversary turtle. How many people here have seen this adversarial turtle before? Okay, a few. So we see a turtle, right? This is a 3D printed turtle. It's not alive, but it's clearly a turtle. And what you probably can't see in the classifiers right there is that the #1 classification that the machine learning network sees, this neural network, is a rifle. So the machine learning network is convinced that this turtle is a rifle. Absolutely convinced. Up to, I think, in the 90 percentiles, depending on the angle. And this was simply 3D printed using standard adversarial techniques within machine learning. We'll get into a little bit of how this works. But of course, this is a massive security issue when we think about using AI or computer vision in real life scenarios, right? And what we have here is an image from a paper from last year on the Dave 2 Nvidia AI system, right? This is supposed to help us drive. And what we can see in ideal conditions on the left, conditions similar to the training data set, that our car drives just fine. And what we see in somewhat natural but adversarial conditions on the right is we're all going to die a fiery death off the side of the highway. And this is pretty awful, right? Because we would like to just sit back and enjoy our nice car design where we just can watch movies and we don't have to think about driving anymore. But this is real adversarial examples that happen naturally just based on the brightness and contrast and the fact that the machine learning algorithm in and of itself, or this model in particular, was not shown these types of dark conditions. So these are obviously problems that we need to fix as we move forward and as we automate more systems using so-called AI or simple machine learning models. But I think a far greater danger to us currently with the way that we currently deploy and build machine learning systems is not necessarily adversarial examples, although they're really fun. It is instead privacy. And the problem is that we feed machine learning models private information on a very regular basis. And within the machine learning community, privacy is seen as something that's pretty hard to do, not saying it isn't, and that maybe we can get to at a later point in time. For security and privacy experts in the room, you're already starting to see the parallels with software development, right? And so what we're going to do is we're going to play a little bit of a game. And in this game, I'm going to pose you several questions. And I want you to think, both in your paranoia security expert brain, but also in your logical brain of what is feasible or possible within computing, and to answer yes or no if you think these scenarios are possible. And we'll do so by a share of hands. Is everyone ready? You awake? Okay, super. So, first scenario. Can I use a machine learning model to figure out if a person is HIV positive? Now you may say, of course, you can use a model trained to determine if somebody's HIV positive. But this is not the scenario. The scenario is that the machine learning model is used, let's say, by a pharmaceutical company or by medical experts to essentially diagnose different treatments for different individuals who are already HIV positive. So this model was trained on data that's a population or a sample of only HIV positive individuals, but it doesn't itself predict HIV positive status. It just does something with treatment classification. So if I have black box access to this API, even limited number of requests, can I determine if a person is HIV positive or not? Raise your hand if you think yes. Raise your hand if you think no. All right. So in a paper released that actually won a privacy award this year, but released a few years ago, Reza Shokri, who's a professor at the University of Singapore, showed that with between 70 to 90% accuracy, he could determine if you, even with incomplete data, were a part of the training data set. So even with black box access, so only API access, limited black box access, because he trained this on machine learning as a service, such as Amazon ML and so forth, that he could determine with between 70 to 90% accuracy whether you were a part of that training data set. Now, a lot of times, training data sets, these are perhaps proprietary. They are often bought and sold. This is not something that is often publicly released, nor before GDPR did we even have a way of querying whether we're a part of a training data set. And I'm not going to get into the overall specifics of this model, but here is essentially the model design. And it uses a standard discriminator practice, which you might be familiar with if you worked ever with GANs. That's all just machine learning speak. But what it does is it can determine, essentially, the confidence that it has seen that information as part of the training data set. And so, indeed, in the scenario presented, if you were a part of that training data set, even if an incomplete amount of your information was a part of your training data set, this is something that I can uncover with high accuracy. All right, second question. Can I figure out your credit card number via a personal natural language processing model, so a personal language model? We can think of this like a predictive keyboard, or we can think of this as there's lots of chatbots now where we essentially try to segregate and group users by similar users or households and so forth. This is because the models tend to work better that way. So if I'm training such a personal chat or language model, can I use that model and extract your credit card number? How many people say yes? How many people say no? How many people say it depends? Okay. So in a paper released earlier this year called The Secret Sharer, what the researchers were able to show is that secrets shown to the model, this is a common model architecture for language called an RNN, or recurrent neural network, and that the idea behind recurrent neural network is it holds long-term and short-term memory, or it holds what we call a gated memory unit, or a gated unit. And this allows us to hold sequence information over time, which makes sense for language, because what you say at the beginning of a sentence and a middle and an end, they all have something to do with one another. And the more information that we can hold relative to the current position that we're in, the better the model works, right? What they were able to show is that using a tree search, they were able to expose secrets that sometimes were exposed only once to the model. Only once. Actual maximum exposure or saturation was at only 10 times. And for strings such as credit card numbers or identity numbers and so forth, these follow a simple pattern, right? This is a simple regex pattern almost that anybody could write, and therefore the search path is not that difficult to ascertain because there's only digits, right? And there's only a certain number of digits. And therefore we can follow the log perplexity, or we can think of this as the highest confidence in order to achieve the highest confidence in the string. Here, a list of digits, which is the secret. And what they were able to use is the Enron data set, and they were able to uncover 3 of the secrets that they were going for in less than an hour. So, don't type your credit card numbers into predictive keyboards. Okay, so can I extract, final one, this one goes out to Lily. Can I extract your face from a facial recognition model? So if you were at Lily's talk earlier, you've heard a little bit about these facial recognition models. Just given access to that model, can I extract your face? Can I essentially reverse engineer what you look like, knowing only your name? How many people say yes? How many people say no? See, I'm slowly having converts in the room. Yes, be skeptical. All right, so what we have here is, I think, the oldest paper, that I'm sharing, which is called a model inversion attack. And a model inversion attack does exactly what you might expect. It essentially tries to invert or expose the internal weights of the model in order to reveal the data. And what we have here on the right is the training data. And I don't know if anybody's used facial recognition models, but this is the AT&T Faces data set, which means it has really awesome hairdos and glasses and fashion from the late 70s, early 80s. Can highly recommend. So this guy, what we can do is we can then use the model that was trained to recognize his face, and all we need is his name. We use his name, and then we essentially use an attack method that allows us to invert the model and achieve the highest confidence. And what we get is the figure on the left, which, of course, is a fuzzy rendition of him. It's how the network sees him. I hate anthropomorphizing neural networks. They don't think, they don't see, they're just numbers, right? But it's how the network sees him, okay? And so if we had no idea how this person looked, we now have quite a good idea of how they look. So, I don't know how many people here go to programming conferences, but there's a series of talks called WTF. And these WTF talks often poke fun at languages and say, like Python, WTF, Golang, WTF, and so forth, right? And they poke fun at inconsistencies or illogical inputs and outputs within languages, because there's plenty, right? Because languages are written by humans, and sometimes we have to make shortcuts. So machine learning, WTF, what is happening? Well, let's talk a little bit, and let's rewind. So let me quick survey. Who here in the room has worked on machine learning beyond just one university course? Okay, a few. And that's fine. We'll go through a brief introduction to how machine learning works. Machine learning tends to work because we're asking for a specific task. Machine learning does not work at all in any type of general AI situation. This is all a bunch of marketing baloney, and beyond Watson, right, this doesn't work by any way, shape, or means. How machine learning generally works is we train it to do a specific thing. Usually we train it to make a prediction, and usually that prediction is within some sort of closed environment. So we can think of predicting a number. We can predict the number of hours that my cat is going to sleep today. We can predict a state. Is my cat awake or asleep? And we can predict essentially the class. Is this a photo of my cat or is this a photo of a cat? When we think about classification problems, what we can often see is decision boundaries. So in this case, we're looking at several different visualizations of decision boundaries. And decision boundaries help machine learning models make decisions, right? If an input comes in and it fits nicely within the decision boundaries, then we have a very clear classification of that input. And what we can see here is that the classification depends greatly on what algorithm you use. So here we have nearest neighbors on the far left, and linear SVM, or support vector machines, and RBF kernel SVM. These are essentially just different algorithms that we're using to attempt to classify what is red and what is blue from the input space. And what we can see is they come up with very different boundaries. And this is two-dimensional, right? But often we're dealing with high-dimensional data, highly dimensional data, of which hundreds, if not thousands, of dimensions, right? So these become very difficult for us to visualize or even think about as humans because we're not used to high-dimensional space, right? And what we can see perhaps here most closely on the nearest neighbor is we have a little bit of what we call overfitting. And overfitting is essentially that we're trying to draw the most perfect line possible between these decision boundaries. And what overfitting tends to do is memorization. And what memorization allows us to do is to extract information that the model has seen before. Because if we start to memorize things that we've seen in the training data set, this means that they are essentially available within the model and can therefore be exploited and extracted via a variety of methods. So let's talk about those methods. How machine learning works, particularly for neural networks, is we use gradient descent. And gradient descent is essentially us trying to minimize error. And we train over time because each round we can minimize more error. And our goal is to go from an area of high uncertainty or high error to an area of low uncertainty and low error. And you can see via this image that we can have multiple paths and that we can end up at what is often called local minimum or local error, right? Local minimum for error. And then there's a global state of error, right? And what we're trying to do is find the global error, but sometimes we find local. Either way, if it works, and we hit deploy, right? But how these attacks often work is they deploy the same methodology. We can start anywhere in input space, and we can simply ask the model, how confident are you that this is your cat? And it says, I'm only half certain. Then we take a step in any direction, and we try to move in the direction that increases confidence. So we're looking for increase in confidence, and this then exposes the training data that this model has essentially memorized. So that's a bit of a general oversimplification of how it works. But let's focus on, when Christian asked me to come speak here, I said, I want to talk about all of these attack methods on attacking models, machine learning models and so forth. Can I do that? And he said, you can do that as long as you tell people how to defend against them. And I said, okay, fine, I'll do that too. So how can we actually protect these models? How can we actually properly protect not only the privacy of the data that we're putting into it, but also the machine learning models against things such as adversarial examples and so forth? Well, I don't think that I am really the expert in the room to tell you how to pen test models. In fact, I'm really hoping and looking forward to conversations after this talk. If you have a long career or experience in pen testing, I want to learn more of your techniques so I can find new ways to attack things that I built. So I hope we can have that conversation after this talk. But beyond, let's say, looking at the more obvious things, such as boundary attacks or API attacks, I/O attacks, these of course need to be secured. Who can access your model? Is your model stored in a secure way? Who can make multiple requests to your model? These are all things that you should think about, and when you deploy machine learning or when the data science people at your company deploy machine learning and they say, don't worry about it, it's just a machine learning model. Now you can go to them and say, okay, we need to still do the same testing on the APIs that you expose. But one evasion technique, or one technique of evading against these types of attacks, both in terms of the privacy attacks as well as the security or adversarial attacks, is to implement something like input sanitization. And so here's one example of input sanitization. Across the top, we have adversarial MNIST digits. These are generated using common adversarial techniques, and MNIST is this digits data set that unfortunately we still use in machine learning for no reason at all other than we've used it for decades. And so across the top, these are images that are often misclassified due to adversarial effects. We can tell even from our human eyes that they have quite a lot of perturbation and noise, and we as humans can see that as noise and focus instead on the actual digit, right? But the machine learning models do not have this compression within their brain, right? They don't think, they can't see things, they can't see patterns the same way that we can by any means. And so one technique against defending about this is to feature squeeze. Or you can also just think of this as any type of compression algorithm or dimensionality reduction. And what we do is we take the noisy and detailed space from the top, and we use dimensionality reduction or compression techniques, and we come up with the much easier to read, if not fuzzy, output on the bottom. And we see that we have essentially reduced quite a lot of the perturbation and noise, and we have something that, although it's fuzzy, scores much higher on the machine learning models because it looks much closer to what it was expecting to see, right? Or what it was expecting to encounter. And as we're on the topic of input sanitization, there's more input sanitization that you can do before you even start training your model. So one thing that I'm working on, I have a company called KI Protect, and we're working on cryptographic pseudonymization. So how can we apply, essentially our goal is how can we apply cryptography and pseudonymization to create an output space that retains as much information as possible without revealing the private data. Because a lot of times in machine learning, we need to use private information. We need to use IP addresses to determine possible anomalies or threats. We need to use locations to determine whether or not somebody is classified as this region or that region. There's numerous things that we need to use that touch upon personal data. And how can we go about doing actual machine learning on this without exposing these people to the privacy issues that we see within machine learning systems that we build today? And we have developed a method that we call homomorphic pseudonymization, which essentially uses streaming cryptography that's prefix preserving. And for the streaming cryptographers in the room, you know that this means that we can retain some of the initial structure within the information. So, for example, for IP addresses, the subnets within the pseudonymized space are preserved. If you use the same key to pseudonymize it, then that same subnets are mapped within the same space. You can use this for feature extraction, such as it came from an internal or an external subnet, and so forth. And so, if you want to talk further about what we're building, or if you're interested in trying out what we're building, we are looking, of course, for beta users. But the main thing is that regardless of what your machine learning engineers say and your data scientists say, and I hate to throw my own community under the bus, just know that if you give them access to all of the data, that means that they feel like they can use all of the data. And so make sure you think about role-based access control when you're giving access to your data science team, because access is important to think about and answer these questions from an entire company level rather than from oh, I made a model that works really well even though it exposes private information. And so my takeaway is really that the robot overlords or machine learning systems that work within your company or at companies that you work with, they need security too. And I don't think this can be achieved only from the machine learning community governing itself or only from the security community trying to govern the machine learning systems that are being used within the company or the service. I think this instead has to be a joint effort, because a lot of people have expertise in different areas, and of course, when we have an interdisciplinary group and we can have conversations, we can often find a more optimal solution that's not completely informed by shutting down the machine learning team, or that's not completely informed by deploying everything that I just built on my notebook into production. And I think there is probably likely a happy medium there. And so it's always nice for me to go to security conferences because I hear a lot of new ideas and get exposed to new things that I don't know about. And maybe some of you will attend some data science or machine learning conferences, and we can have a much greater conversation, not only as we continue conversations today, but over the years as we deploy more and more machine learning systems. Thank you so much. If you have questions now, I'll take some. If you want to reach out later, you can reach out to me via email, or I have open DMs on Twitter. You can chat with me anytime. Thank you so much for your attention.
Where do we have questions? Raphael, of course. Mike is coming.
Thank you. Very interesting talk. I wonder about the utility of the homomorphic pseudonymization. So, I mean, I don't want to be too technical right now, but essentially this has to be a continuous function, because otherwise, if you apply the model that you have trained based on the pseudonymized data, then the information you get out of the model has to be like inverted, right? And so for this goal, you need to have a continuous function, because otherwise if you map Berlin to Leipzig, well, good, but what if you get a city like Fulda or whatever, and what do you map this to? So it has to be invertible, this function. And my question then is, how do you preserve the utility of the network, which should be the main goal of it, right?
Of course, yes. Sorry, I did not get into this, but all of this can also be, the pseudonymized values can be mapped back to the raw input space via the same cryptographic process with a key. So the idea is that you deploy the pseudonymized, but that this interacts with a secure system that can also decrypt the information and then make some sort of decision based on the decrypted target or something. This also, sorry, one other quick thing, is that we've tested this with numerous deep learning frameworks. We've done some work with the DCSO, the German cybersecurity organization, on threat modeling via anomaly detection of their network net flow data. We presented this actually at RIPE 77 last week or the week before, which is the European Internet Service Provider Network. But we also have a technical white paper that I'm happy to send you, and we can chat further. Yeah.
Yes, please, because
it
has always been a challenge to have a bijection, right? Because encryption gives you bijection, but sometimes this is meaningless.
Yeah.
And I'd really like to look into this.
Thank you.
Very interesting.
Sounds awesome. Thank you.
Good. What other questions do we have? There was such an advanced one, nobody else is daring to speak up anymore. There is, yeah, Katherine.
Oh.
You're sitting so much on the left I never see you.
I wondered about re-identification attacks on the anonymized data by merging it with non-anonymized data. If someone leaks a related set, do you see those that re-identification being possible?
Yeah, of course. So linkage attacks and statistical attacks on de-anonymization are heavily documented, let's just say, and are quite possible. And we have a continuous trade-off between privacy and utility. So this is something that I talk about a lot within the machine learning community and data science community, is how can we find along this continuum of fully private, which fully private is deleted data, right? This is fully private, is completely removed, right? And fully raw data is, has a lot of privacy issues. But we see that there's a kind of a continuum there. I think a lot of people, probably similar to security, think of privacy as on or off, which is like a very artificial dichotomy, right? Because security on and off or privacy on and off, this loses the fact that there's probably multiple layers and multiple attack vectors. And so when we look at linkage attacks, which is what you're referring to, these are quite common, right? This was de-anonymization of the Netflix data set, was the first widely publicized linkage attack. But these are quite common, and the only way that we can get around this is implementation of more strict privacy methodology, such as differential privacy. And differentially private machine learning models are possible, but they still can potentially sometimes reveal information depending on how they're trained. And I can point you to numerous research on the topic and so forth. It's a fun space, and it is something we're also working on. So we're working on a differentially private event stream aggregator that essentially allows you to make differentially private queries, which, yeah, if you don't know what differential privacy is probably, but we can talk about it.
Very good. Scanning the room. Additional question?
I just have to point out that I did trick Facebook into thinking I wasn't a person. So this was from my talk. I gave a talk at 34C3 on adversarial image recognition, and thought a shout out to Lily and her awesome talk earlier is using the standard fast gradient sign method, which is a standard attack from adversarial machine learning. I was able to convince Facebook that I was not a person.
Good. Let me ask a final question myself. You presented several research papers, and that sounded quite believable. How close are we to seeing these attacks in the real world? I mean, machine learning models are deployed in the real world now. How close are we to having our credit card stolen via machine learning?
I mean, I feel like this is probably difficult to say because I don't necessarily know a lot of people that are working, let's say, to sell people's private information on the internet. But what I can say is that most of the papers that got recognized and published within the past year were focusing on these massive machine learning as a service and how easy it is when you use these massive machine learning as a service, such as Google ML and Amazon ML, and you upload the data there, that these models leak quite a lot of information by default. So similar to what Lily said earlier, we don't necessarily, if it wasn't published in research and it wasn't validated essentially on the open data sets that we know, we do not know the underlying algorithms that a lot of these use. And most of them actually underperform even a simple training yourself. So I guess if you're going to use machine learning as a service, you should be asking lots of questions and be testing how it actually works and is deployed. And if you're going to build it yourself, then you should go through some sort of automated testing and automated security testing on a regular basis.
Wonderful. Thank you for your estimation. I have chocolate for you.
Thank you so much.
Thank you for coming here.